Hello, and welcome to our video covering the image and kernel of a linear transformation. Let's start with the image. So the image is something you already know about it. You've been calling it the range in every previous class that you've had. But at some point, mathematicians decide to start calling the range the image in more abstract functions. Don't ask me why. So the definition that your book gives of the image is, the image of a function is all of the values the function takes in its target space. And then they give some set builder notation for it. The image is just, if you have x in your domain, then it's a set of f of x's. And another way to write that is just if b is in your codomain, then it's got to be in the, if b is in your codomain, it's got to be a b such that it is equal to some f of x. So it's really the set of outputs of your function, or the set of solutions to the equation b equals f of x. So like I said, you know this already. Your book, if you're talking about finite sets, you've got your domain, and then what it calls the image is just, it's the range. It's the set of outputs of your function. And even more familiar to you is something like this. If you have some function e to the x, then what's the range? What's the set of outputs? What's the image? Well, it's, as you can see, it's going to be all y values that go from 0 to infinity, but don't include 0. So it's just positive real numbers. But I didn't mention this to go over things you already know. In this class, we are interested in what is the image or range of a matrix or a linear transformation. So let's look at an example. Let's take a specific linear transformation that is represented by the matrix A, 1, 2, 3, 6. So what is the image of this linear transformation? What are the possible set of outputs? Well, okay, let's think about it. Like this matrix times some random vector x it's going to look like this. And if we look at the kind of column picture of this, we say, all right, this multiplication is just equal to x times the first column, x1 times the first column, plus x2 times the second column. And then you might notice here that 3, 6 is actually a multiple of 1, 2. And so we could rewrite this as x1, 1, 2 plus 3x2 times 1, 2. And then we can kind of group these coefficients and write the solution like this. Geometrically, what this gives us is actually a line. This is the span I don't know if I've defined span yet. This is the set of all multiples of the line 1, 2, of the vector 1, 2. If you just stopped here, you'd say, it's the set of multiples of the vector 1, 2 plus any multiples of the vector 3, 6. But since 3, 6 is parallel to 1, 2, it's really just this line. So this line through the origin is the image. Okay, let's keep pumping our intuition about what the image of a matrix should look like. In this example, we've got, this isn't a square matrix. It's a matrix 1, 1, 1 and 1, 2, 3. These columns are, this column here is not a multiple of the first column. So let's see what we have in this situation. So here, now the image, is all of the vectors of the form. You're taking all right, here we're like starting with the linear transformation, not the matrix. But the linear transformation, what are this? You take a random input vector. What does the output look like? This transformation is just multiplication by the matrix A. Again, we look at the column picture of this. And here it looks like we have to look at all of the multiples of this vector 1, 1, 1 added to all of the multiples of the vector 1, 2, 3. So another way of saying this is just all linear combinations of the column vectors of A. In a geometric form, this is going to look like a plane through the origin. So you've got two vectors and you're looking at all linear combinations of these vectors. And this actually is going to generally how we think about this can be how we generally think about the image of a matrix. It's going to be, the linear combinations of its column vectors. And before I guess I say that officially, let me note just that in this example, we're saying, when we say that the image is, say, a plane like this right here, what we're saying is that all possible solutions of our system, of like the matrix AX equals something, what could AX equal? It's got to equal something in this plane. This is the set of possible solutions to AX equals B. So if you had some vector B like this that's not in that plane, that's not in the image, then this vector B will make AX equals B inconsistent. So, okay, that's good to keep in mind. We will see things like this again and again throughout the term. So, okay, the image or range of a matrix or linear transformation versus the column space. The column space you saw in that 3 blue, 1 brown video. Turns out they're the same. But first, the last two examples were motivating this definition that your book gives of the span. So the span of a set of vectors refers to the set of all linear combinations of those vectors. So as we saw in the last example, the image of a matrix, we saw it as the set of all linear combinations of the columns of that matrix. So, okay, we end up talking about the set of all linear combinations of some set of vectors enough to give it its own name. And we call that the span. And then it is a theorem. Oh, whoops. Okay, before I got a little ahead of myself. So the span, written span, parentheses, your set of vectors. That is the set of all linear combinations of the vectors. Okay. And now it is a theorem that the image of a linear transformation, that is the range of your matrix, is the span of the column vectors of the matrix. So this is, some books start with just this notion of the column space. And this really is the set of linear combinations of the columns of the matrix, or the span of the columns of the matrix. That's how some books just start there, and they define that to be the column space. So yeah, the span of the columns of the matrix, also called the column space. So some books start there and just say, by definition, you've got this notion of a column space, and then show that it's the equal to the range. And your book starts with the range and then as a theorem says, the range has to be the set of linear combinations. And then you can call that set of linear combinations the column space. But your book doesn't actually, while it mentions that other books call it the column space, in your book, it's just going to keep calling this the image. So yeah, we're going to stick with your book and continue to call, instead of the column space, we will call the image. We will refer to the span of the columns of your matrix. We will refer to that as the image. I feel like I've talked too much on this slide. Let's continue. Okay, so now the kernel. This is what that 3 blue, 1 brown video was referring to as the null space. And you'll see both kernel and null space in various books. I happen to prefer column space and null space to image and kernel, but I did not write your textbook. So, okay, let's just get the formal definition of the kernel out there. The kernel of a linear transformation from Rm to Rn consists of all zeros of the transformation. So it's the set of vectors that get sent to zero by the matrix or your linear transformation. So yeah, another way of saying that is the kernel is the set of vectors x such that ax equals 0. It's the solution set, I guess, to ax equals 0. So your book gives this, I keep wanting to call it the image, but it's like, no, image is something else here. It gives this figure, there we go, where it is, okay, it's deciding that Rm and Rn are now just represented by balls for some reason. But the reason I bring this up is because it makes clear where the image and kernel live when you're thinking about the domain and the target space or the codomain. And so the image is a subset of your codomain or your target space. It's where everything gets sent. It's the set of possible solutions and set of possible outputs, whereas the kernel is a subset of your domain. It's everything in your domain that got sent to 0. So that's just good visualization to keep in mind. The kernel and the image live in different spaces. Okay, now let's do an example. Just given our definition of a kernel, let's find the kernel of a linear transformation. So here we've got this transformation that's represented by multiplication by this matrix. It's a function from R3 to R2. So our kernel should be a three-dimensional vector, or should consist of a set of three-dimensional vectors. So the key to finding the kernel is realizing that, okay, if the kernel is everything that gets sent to 0, then you have to solve the system ax equals 0. And the set of x's that solve this, that is your kernel. So, okay, let's do it. The way we solve the system ax equals 0 is you make this augmented matrix. You have your matrix A, and then you have the constant vector 0 on the right of the vertical line. And then, all right, you refify it. When you find the reduced row echelon form, it's of this form. I'm not like doing these calculations by hand. I assume you know how to find the reduced row echelon form at this point. And then, okay, now that you've got your matrix or your augmented matrix in reduced row echelon form, translate this back into equations. So, okay, if this x here was, it's a three-dimensional vector, x1, x2, x3, then translating this back into equations will be x1 minus x3 equals 0 and x2 plus 2x3 equals 0. And then, all right, let's solve for our leading variables, x1 and x2, and now we can parameterize or vectorize our solution set. I like vector form of solutions better than parametric form because just respects the geometry of the solution. And so, okay, we've found the kernel. It's all x1, x2, x3 vectors that are multiples of the vector 1, -2, and 1. So we could actually write the kernel as a span, just like we wrote the image as the span of some vectors. The kernel is the span of this vector 1, -2, 1. Like normally you think of linear combinations as having multiple vectors, but okay, if you just have one vector, the set of linear combinations is just the set of multiples of that vector. And this is actually something that's going to be true in general, is that we can always describe the kernel as the span of a set of vectors. And the reason that ends up being true, this is going to be totally hand-wavy here, but the reason it's true is because here, when you were, I guess, let's go back. You're always when you're finding the kernel, you're trying to solve this system of this linear system, ax equals 0. And because you have a 0 here, which means your final column is going to be the 0 column, when you do your reduced row echelon form, you're still going to have a 0 column here, which means when you translate back, you're going to have zeros on the right-hand side, which means when you solve for your leading variables, it's just going to be parameters on the right-hand side. You're not going to have a constant vector. And so you don't have any, so what you end up with is just parameters times vectors, and that will give you the span of the vectors that your parameters are multiplied by. Okay, let's end with some facts about the kernel. And actually kind of like the way your book phrases this. When is the kernel equal to 0? So if we can get our minds around this, I think it'll be a good indication that we've understood some fundamental things about the kernel. So when is it the case that you can, when, like what matrices make it such that their kernel is equal to 0? So first, your book says, all right, let's consider a general n by m matrix. Your book claims the kernel is 0 if and only if the rank of the matrix is m. So this is saying the kernel is 0 if and only if the number of leading ones is equal to the number of columns. And so let's think about why this is true. So if, I guess, let's start here. If rank A is m, so if the number of leading ones is equal to the number of columns, then when you're solving that system, ax equals 0, you have just, you don't have any free variables. So it's just x1 equals 0, x2 equals 0, all the way down to, now you're, if you're doing it for every column, that's every variable. You get every variable equals 0. And so solving that system, the only solution is the 0 vector. So that's going that way. Starting from if the kernel is 0, why does that mean that the rank has to be m? And I think the idea here is just that, okay, well, if the rank wasn't m, then the kernel couldn't have been 0, because if the rank's not m, then you've got a free variable. And you have, if you've got a free variable, then the kernel is going to, you're going to have a parameter and a vector multiplied by that parameter, and the kernel is not going to be 0. Which I think is kind of what the next thing says. So yeah, if you have an n by n matrix and the kernel, if the kernel is 0, then, oh, this is slightly different actually, but okay, if the kernel is 0, then your book says the number of columns has to be less than or equal to the number of rows. And then they say equivalently, if the number of columns is bigger than the number of rows, then there are non-zero vectors in the kernel. And this is, like I was saying, if the number of columns is bigger than the number of rows, then you have one of your variables has to be a free variable, because the number of leading ones can't be bigger than the number of rows or columns. And so if you have more columns than rows, you have at most n leading ones, which means you've got to have some free variables, which means you've got some non-zero vectors in the kernel. Because when you set up that ax equals 0, you're going to have parameters and vectors that they're multiplied by. All right. Finally, something that this gets used a lot. Suppose you have a square matrix. When is the kernel 0? Well, if you have a square matrix, the kernel is 0 if and only if the matrix is invertible. So this kind of follows from what we had before, except now it's an n by n matrix. And so the yeah, you're going to have the kernel being 0 if and only if, okay, the matrix has full rank. And that just means, we've seen before that full rank means that the matrix is invertible. And that's an if and only if. So yeah, well, I'll just reiterate, this last one is a nice theoretical test for when we have a linear transformation, whether that linear transformation is invertible or not. So for things like matrices that we just have a physical matrix in front of us, then okay, we're not maybe going to use this test because we'll just solve for the kernel. But when we're thinking in general, this last one ends up being useful. All right. I think that's all I wanted to say. See you in the next video.